Welcome! In this video I will show you how to solve problem 4.20 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. Now this problem states the following. It says, starting with the canonical commutation relations for position and momentum equation, well, that used to be 4.10, work out the following commutators. So basically all the ones that we have there. Then we will use the results in part B to obtain that other commutator and then evaluate some more commutators and then show that the Hamiltonian commutes with all three components of L, provided that the potential depends only on R. So that is what we're going to do. Okay, so this is the reminder. So basically we have to remember what the commutators are between position and momentum, and also between position and position and momentum. So basically here, keep in mind also what the commutators mean. So on one hand, a commutator tells you if two observables are compatible. So that means, can you know the value of one observable at the same time as another? So that is more of a physical interpretation. But also it has a more mathematical meaning, and that is basically, can you switch both of our quantities, right? If you have x times p, for example, can you just change it and write p times x or not, right? So those are two meanings of the commutators. And what we know already are these. So we know that position and momentum have a factor, so they do not commute. They are a factor of iℏ bar as long as we are talking about the same direction. So for example, x and px do not commute, but x and py or pz do commute, right? So that's what we are representing here with this delta. And whenever you have a commutator, that's very important. Keep in mind that you can change the order of the things that are inside by putting a minus sign outside. So you're basically factoring out a minus. So that's a very important property that you should remember. And position and momentum with itself, it of course commutes. You can always write x times y or y times x. That fortunately is not an issue. Okay, so with that in mind, let us actually go ahead and work with part A. So we want to prove all of those commutators. So part A, let's begin. So let's begin with the commutator of Lz, x. Okay, so that's the angular momentum, or the z component of the angular momentum. Okay, so how do we calculate this? Well, let's write out what the angular momentum in the z direction is. So this is x py minus y px comma x. Okay, now we're going to use properties of the commutators. This is a very nice problem to practice commutator properties. So what we will do is that we will separate this into two different commutators. So what we can do is write this as x py comma x and then minus y px comma x. Okay, and now we're going to use another property, and this is very important. So use this property, and this is one that you should really remember. It's not super difficult to derive if you need to, but if you are learning this topic in school, I do recommend that you know this quite well. So it is as follows. If we have a comma bc, so the commutator of a and then two things on the other side, this is the same as the commutator of a and b times c plus the commutator of b, plus b times the commutator of ac. So this is very important. And there's a similar one, which is ab comma c. So you have two things in the front and then you have the other. So in this case, what you have is that you take the a up front here, and then you get b comma c plus, and now once again, you take b just like we did here, but now we're going to put it on the other side. So we also get a comma c, but now b is on the right side. So this is also very important to know. Okay, so these are very, very useful properties. So you can also, by the way, quickly check if that they're actually true by just multiplying through here. So for example, let's just do the first one. That would be ABC minus BCA. And then if you go through those commutators there, you get ABC minus BAC plus BAC minus, and then we get B, C, A. So these two cancel out, and we are left with exactly what we had on the left-hand side. And that is exactly how this is actually derived. What you usually do is that you write this out as ABC, and then you just add a 0, and then you can form the other two commutators. So now that we know where that comes from, let's actually use it. So now we have, plugging it here, that would be x, comma, so write A, B, C. So this would be, let's see, this one right here requires us to use this property. And that would mean that we have x outside, and then we have pi y comma x minus, plus, and then we get AC. So that would be the first and the last. So that would be x comma x. And then we multiply this by b, which is py. Then we do the same thing for this one. So that would be minus y px comma x minus, and then we have again AC. So that would be commutator between y and x, and we multiply by px. So now let's evaluate these commutators. So this one right here is simply 0, right? X commutes with x. It also commutes with y. So those quantities are 0. Then we have the commutator between py and x, right? Momentum in the y direction and x. So let's go back to our expression. We know that x comma p, or xi_pj, is iℏ bar times delta ij. So that means that it is only non-zero when I and j are the same. But we have x and y, which are not the same, so this is 0. And then we have this quantity right here, which is indeed, it is the same, but it's not written like here. So we're going to have to switch the order of the commutator by putting a minus in front. So that's going to mean we have minus y times x comma px. And now we can use what we had up there, which means that this thing is going to be iℏ bar times y. So this was Lz comma x. So that is the first one. Now we're going to do the same thing for, well, Lz comma y and then Lz comma z. So let's do Lz comma y. So we have Lz comma y. So this thing right here, again, we're going to do the exact same thing. So we write it out, and we have Lz, which is x py minus y px comma y. So once again, we're going to separate this commutator, and we write it as x py comma y minus the commutator of y px comma y. Okay, so what do we have here? Let's again use the property that we have up here in blue. And let's see. So the x will go outside, so we get x py comma y, and then we have plus, and now we get a and c. So that means x comma y and py. Okay, now for the second one. Here we have minus y px comma y minus y comma y px. So once again, let's evaluate these commutators. So these ones commute, this commutes, so that's 0. Then we have px comma y, that is delta ij, where I and j are different, so that means that this is also 0. So we're left only with this one. So here we have Lz, maybe I'll stick to the same color, I don't want to make this confusing. So that's Lz comma y, this is x, and now let's switch the order here, so minus x, y comma py, and just like before, this is iℏ bar delta ij, but delta is going to be 1, so this will be minus iℏ bar times x. Okay, now let's do the next case. So now we have Lz comma z. So here we have now Lz comma z. Well, again, let's write out what the angular momentum in the z direction is, that is iℏpy minus iℏpx, comma z. We separate the commutators, so iℏpy, comma z minus iℏpx, comma z. And now, what do we do? Exactly the same as before. So you can see that the procedure is really doing the same thing over and over again, just that some of the commutators at the end will be a bit different. So this would be iℏpy, comma z plus x, comma z py minus iℏpx, comma z minus y, comma z px. So this is 0, right? Delta ij, they are different, 0. These commute, 0. Delta ij different, 0. These ones commute, 0. So this thing is 0, exactly like we wanted. So those are the first 3. Then we have Lz, comma px. So let's do that. So now we have the commutator of Lz, comma px. So again, let's do the exact same thing. So this would be iℏpy minus iℏpx, comma px. So you can see that the procedure is really just doing the exact same thing all the time. And now we have iℏpy, comma px minus iℏpx, comma px. So now let's again separate this. So we get iℏpy, comma px plus iℏpx py minus, and then we get iℏpx, comma px minus iℏpx px. Okay. So now we have all these commutators of momentum. So let's go refresh that. So just like position, momentum commutes. And that of course makes sense because they are simply spatial derivatives. And we know that the derivative with respect to x, y, or z, they simply commute. It doesn't really matter in which order you are applying those derivatives. So that means that this thing right here, it is 0. And now py, px also doesn't matter, 0. iℏpx, that is delta ij different, 0. So the only non-zero part comes from xpx, which we know already is 1 iℏ bar, and then we get py. So there we go, that is that result. Let's go for the next one. So now we have to do Lz_py. Okay, so Lz_py. So here we are going to start off again, exactly the same. This is just basically the same procedure over and over again. So again, we separate this. So iℏpy, comma py minus iℏpx, comma py. Now we separate this. This is iℏpy, comma py plus x, comma py minus iℏpx py minus, and here finally we have this would be py px. Okay, so again, momentums here, they commute, this commutes. Here we have delta ij, they are different, so this is 0. So the only non-zero part comes from this here, iℏpy, so there we get minus iℏ bar px. So next we want to calculate Lz pz. So here what we're going to do is, well, the same. Surprise, surprise. So xpy minus ypx, comma pz, we separate this into xpy, comma pz minus ypx, comma pz. And again, we use the same property. We separate these commutators, or we take this factor out. So we get xpy pz. This is just a very common thing to do. We want to have a commutator of two things. We don't like it when there's a third one in between. So plus, this would be x pz py minus y px pz minus y pz px. Okay, so again, let's see. Momentums, they just commute, so that's 0. This is 0. This right here, delta ij, not the same, so 0. And this thing also delta ij different, so this entire thing is simply 0. So there we go. We just finished part A. As you can see, it's just applying properties of commutators over and over and over again until we can arrive at commutators that we can easily solve. So part B asks us to find this commutator using the previous results. So what you could do would be to write this as LZ being x py minus y px and Lx being y pz minus z py. And then you could separate this into 4 different commutators like we just did before, and then just use again the property to remove one of the elements from the commutator so that you can reduce it into the basic commutators between x and p and x and p, and then you find the value. That is perfectly valid, but it's going to be a lot longer than it has to be because we already calculated quite a few of these combinations. So since we already know how LZ commutes with all of these elements, well, let's just write this as LZ. So let's now separate this. So we get the commutator LZ, y pz minus LZ, z py. So now, again, let's remove one of these elements. Note, however, that now we have the other expression that I wrote up here. So far, we had been using the lower one of the two. So now we need to use the upper one. So a comma b and c is removed there. And then we have ac with b on the other side than it was before. So let's do it. So that means that we get LZ, y, and now we take the PZ outside, but to make up for it, we need to add the commutator with now the B element, so Y out here, and LZ, PZ. And then we have minus LZ, Z with PY outside, and then we have minus LZ, py, and z is here. Okay, so now let's not really calculate. We already found each one of those expressions. So let's see, LZ, pz, this one right here, we know is 0, right? That's a previous result. LZ, py, this thing right here we know, so let's write it down here. That is 0. This thing right here is minus iℏpx. So we get plus z iℏpx. Then we have minus LZ, z. That one was also 0. And then we have LZ, y. So LZ, y is minus iℏx. So this is minus iℏx times pz. So here we can factor out iℏ bar, and we are left with z px minus x pz, and that you might recognize is simply Ly. So there we go, that is our result. This is exactly what we wanted to prove. Okay, so part C now wants us to calculate this, or rather these two commutators, where r squared and p squared are as given there. So let's begin with the first one. So the commutator between LZ and r squared is simply going to be the commutator of LZ and, well, what is r squared? R squared is x squared plus y squared plus z squared. So here we are simply going to now separate this into 3 different commutators. So LZ, x squared plus Lz comma y squared plus Lz comma z squared. Okay, and now we are going to write each one in the following way. So this is going to be x times x, this is going to be y times y, and z squared is going to be z times z. And the reason why we do that is because that way it becomes much more apparent that we once again want to use the same property of separating the commutator, or rather taking an element out of it. So the first one would be Lz comma x times x plus, and then we have the commutator of Lz and x and an x over here. Okay, now this one, this would be, well, the same but with a y. So Lz comma y, y plus y, Lz comma y. And finally we have the same but with a z. So Lz comma z times z plus z times Lz comma z. And we know what each one of these are. We calculated them at the start. So Lz comma z is 0. Lz comma y and Lz comma x we already found. So Lz comma x was iℏ bar y, and then we have the x, then we have plus x, and this commutator is again iℏ bar y. And what else do we have? We have this other commutator which we already found, and it is minus iℏ bar times x. And finally here we have plus y times minus iℏ bar times x. So now remember that x and y commute, so that means that you can just switch their position and nothing happens. So we have minus iℏ bar xy, iℏ bar xy. So this and this cancel out. And then we have minus iℏ bar yx, iℏ bar yx. Well, that's also going to cancel out, so you end up getting 0. So this indeed does commute. Okay, now let's do the following. Let's now go for the second one, which is Lz comma p squared. So again, let's write it out. So this would be Lz comma px squared plus py squared plus pz squared. And we're going to do the exact same thing. So Lz comma, and let's just write it out as px right away, plus Lz comma py plus Lz comma pz. Okay, now again we separate this as Lz comma px with a px outside plus px, and then we get Lz comma px plus, and here we have again Lz comma py plus py Lz py. I'm just using the exact same property I've been using the entire time of just removing an object from the commutator. And finally we have Lz pz times pz plus pz Lz pz. Okay, so with this we can now find what this actually is. So Lz pz, which is right here, we know is 0. So this thing is 0, this thing is 0. Okay, then we have Lz py, or maybe let's go here in order. So Lz px we found is iℏ bar py, and there is still a px here, so px. Then we have plus px, the same thing, so iℏ bar py. Then we have Lz py. Lz py is going to be minus iℏ bar px. And then we have plus py minus iℏ bar px. So again, just like before, all of these things are going to cancel out. iℏ bar py px, you can just commute them. So that's going to cancel out with, well, any of these. This is already in the same order, so maybe you can use that, or you can commute them py and px commute, so you can just change the order and it still works. And those two cancel out. So we get 0. So both of these commutators are 0, so that means that those quantities commute. Okay, so part D says this. It says, show that the Hamiltonian given by p squared over 2m plus v commutes with all three components of L, provided that the potential depends only on R. That means that the Hamiltonian L squared and Lz are mutually compatible observables. Okay, so let's prove that. So what we're going to do is write our L, comma, H. Okay, and which component? Well, let's begin with Lz. Now you could use any of the three and the procedure will be exactly the same. I'm just going to do this once because it's relatively long and nothing changes between doing it with X and Y, except that, well, the letters will be different, right? But the procedure will be literally the same. Okay, so this thing right here would be Lz, comma, and now let's write what H is. So that's p squared over 2m plus v, which, just as a reminder, is a function of R. So here you can separate this. So this would be the commutator of Lz, comma, p squared over 2m. And this would be plus Vr, so sorry, this would be plus the commutator of Lz and Vr. Okay, so the first commutator is 0. We have already shown it, right? It's what we literally just showed. The factor of 2m doesn't do anything. It's a constant. You might as well just factor it out. So that part is 0. So there's nothing new there. Now this part is a lot more interesting. Now there are some properties that you can use to kind of show that it's obvious, but I don't like doing that. I'm just going to show you the hard way what this actually ends up being. So I'm going to drop the dependence on R just so that I don't have to write that much. So let's continue. Now I'm going to write Lz as iℏpy minus iℏpx and v simply as v, right? The potential simply as v. And now I'm also going to write the momentum in this way. So I'm going to write it as h bar over I dy minus y h bar over I dx. Okay, and now I'm going to let all of this act on a trial function or a test function. So that's something that is very important that you have to do. When you're evaluating commutators and you have derivatives and things that actually affect your function, it's very important that you use just a test function, right? Just a function that you write there so that when you apply the derivative, you keep in mind that you are going to have to use the chain rule, and then you're actually going to find the result, and then you just drop the function at the end. You're going to see what that looks like in just a moment. So let's now separate this commutator again. So this would be x h bar over I dy comma v, and then we have minus, I guess we could take the h bar over I outside, but whatever, dx comma the potential, and of course this is acting on the function, and so is this. Okay, so now let's write out the commutators. So this would be h bar over I. Actually, I'm going to just factor it out. I don't want to have to deal with that all the time. So h bar over I, factor of everything. So this would be x dy, and now this is very, 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 very important for you to consider. Here we're going to have this thing acting on all of that, right? So that would be derivative of vf, very important, minus v times x, and now the derivative of just the function dy. And now we have the second part right here, which is going to be minus y, derivative with respect to x of vf. This parenthesis is super important. Do not forget it. And then we have minus, so minus minus, so plus. And that would be v times y dx, and this is of simply our function. So let's now apply our derivatives. So this is now h bar over I, and now we have x times, and now we apply the product rule. I think I said the chain rule before, I meant to say product. So this would be dv dy times f plus xv df dy. So this is very important. This is why we use this trial function. Otherwise, this term there wouldn't exist at all. So this is now minus vx df dy. And then we have this part, which is minus y dv dx times the function plus we still have to apply the product rule. So we get minus y v df dx plus vy df dx. Okay, so now let's take a look at what we have here. So x dv dy f xv minus vx xv. V is simply it is a function of r, and r is a function of the coordinates x, y, and z. So x and v, they simply commute, so you can change the order, and this will cancel out. Similarly, we're going to get that this and this will cancel out, so that and that cancels out. So all we are left with are going to be the other two terms, so h bar over I, and then we get x dv dy times f minus y dv dx times f. Now we're going to use a little bit of a trick. And what we're going to do is the following. We're going to now write this as dv dr times dr dy minus y dv dr times dr dx. Okay, and by doing this, we can now easily calculate dr dy and dr dx, because we know that r is going to be the square root of x squared plus y squared plus z squared. So dr dy is going to be 2y divided by 2 times the square root of the exact same thing. And well, I guess the 2's cancel out, so we can just remove them. And similarly, dr dx is going to be x over x squared plus y squared plus z squared. And we can now plug it back in. And we can also factor out this dv dr, right? It commutes with x and y, so there's no problem there. This is going to be dv dr, and we are left with x, and then this quantity right here, which we calculated, that is simply y over the square root of x squared plus y squared plus z squared minus y times x divided by the square root of x squared plus y squared plus z squared. And all this is equal to 0, right? We have the exact same thing. So there we go. This commutator is 0. And you can now do the exact same thing, but for the other. So instead of having LZ, you can write this as LX. So that would be, well, YPZ minus ZPY, and you do the exact same thing. So that's why I'm not going to do it, because it would be to do the same thing 3 times, and I don't think that it makes any sense. So yeah, that's all we had to do. This entire problem was mainly just practicing over and over using the basic properties of commutators and remembering what the expressions for momentum are. So yeah, I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. I'm going to upload the notes. So all that I just wrote, it's going to go all the way to a drive, a folder, in a shared folder in my Patreon. So if you want to access this and also support me, then yeah, do go check it out. So I'll see you in another video. Thank you very much for watching.